So hello everyone. Now let's move forward to the remaining type of number which we haven't discussed, and is irrational number. So as you can see today, this is a type which we want to understand, and these are some important categories in this. And this is our aim for the lecture, that we'll try to identify what are these numbers, and this we have already covered. What were natural numbers, what were integers, what were whole numbers, what were rationals. And so I suggest you who are watching this video, if they haven't watched the previous one, then refer to the part 2, types of numbers. Fine. So now let's try to understand. Let me rub this. Let's try to understand the topic of today, which is irrational numbers. One more thing, you observe that there is some triangle which is there in the picture today, which was not anywhere in the previous lectures. So, as in the previous lecture, you observe there were some numbers in the blue which I have just pointed out few of them. They are rationals, and there are of course infinitely many which we have already answered in the previous lecture. So, what are irrational numbers? Definition: a number which is not rational Fine. So, a number which is not rational is called an irrational number. Rational was rational or simply fraction was which can be expressed as a ratio of two integers p by q, where of course q is not 0, and those numbers which cannot be expressed in that particular form, they are called irrational numbers. Fine. Observe one more thing. The rational numbers which you have studied already in the previous lecture have some decimal representation, and that representation terminates after some places. What I mean by that, so let me take an example. The fraction is 3 by 4 and has this as its decimal representation, which you can find easily by ordinary division. You observe that this decimal terminated after these two places. Fine. Let's take another example. 1 by 3. If you try to observe it decimal representation, 0.333333, and it goes on with infinite string of threes. This is the string. This I am calling this as the string of threes. After 1 there is another 3, so this is repeating. Fine. And you observe that it is repeating with the same sequence. So there were basically two types of fractions, either that will terminate or that will not terminate. So the one which is not terminate is following a pattern. Fine. Now there is a problem which we have to answer. What are irrational numbers? So for that, I'll use this triangle. And one more important definition I'll be using is Pythagoras Theorem. So let me run all of this. So you got a clarity what is an irrational number which is not rational. So now if I apply the Pythagoras theorem on this right angle triangle, so let me name these sides. Suppose this is x, this is y, and this is z. This one, the hypotenuse. So we know by Pythagoras theorem that z square equals to x square plus y square. X and y in our case are 1 and 2 respectively, so this will reduce to 1 square plus 2 square. 5. So now the problem reduces to solving z square equal to 5, or simply the quadratic equation z square minus 5 equals. Let me rub this one. We don't need this. So the problem reduces to z square minus 5 equals to 0. Now using the basics of identities which we have learned, a square minus b square. So can I now rewrite, if you convince yourself, can I now rewrite z as like something like this. Can I rewrite it like this? Root 5 means, this root 5 means 5 raised to the power half. In general, root x means x raised to the power half. Fine? This root means raised to the power half. So this will nothing but a minus b and a plus b. So that will come out to be, this fraction will be 0 or this fraction will be 0. What I will say, this part of this. Fine? This factor. Either this factor will be 0 or that factor will be 0. So z equals to root 5 from the first case and z equals to minus root 5. But this can't be whole. This cannot be whole. Pause the video and think it once. Why? The answer is so simple, because that is the side of this triangle and which is of course its length, and length is always positive. So length cannot be negative. So that's why this cannot hold. So only what reduces to this has to be root 5. But observe now again, there's a problem. This number which we have just encountered with square root of 5 is not present in any of the previous discussions. Like it is not a natural number. We didn't find it anywhere in that list. It is not a whole number. It is not an integer. It is of course not a rational number. If root 5 would have been a rational number, then if root 5 was a rational number, then root 5 would be equal to some p by q. Integers, and q cannot be 0. But it's not possible for any choice of p and q from the list, from this list. There is no p and q belongs to the list of integers for which this expression holds. That is, this is not a rational number. So therefore they cannot hold, they are not equal. And to give it, we're going to give its proof when we'll be discussing the problems based on the exercises for rational numbers, irrational numbers. When we are doing the exercises, then I'll be going to prove how it's not equal. Fine. So there are two more important points which are now need to be discussed. The first is, this is the main characteristics of an irrational number. The first is the decimal expansion. If we recall, in case of rational number, they do also have decimal expansions, but they terminate after a finite number. They, like, their decimal expansions terminate, or if they don't terminate, they might repeat. But in case of irrational number, what the first point says, the decimal expansion does not terminate, it goes on after the decimal. And the second is nor and with a repeating sequence. Nor and with a repeating sequence means there is no specific pattern after the decimal representation in the expansion of an irrational number. So so now we can rub this. Some important irrational numbers which you will going to encounter throughout this chapter is, the first is pi. Let me use some another pen. Important irrational numbers. Important examples of irrational number are pi, like root 2, root 3, root 5, this kind of numbers. There's one more number called e, exponential, but you might not use this. So all these numbers, etc., there might some more. There are some other irrational numbers. So these are major types of irrational numbers which we're going to encounter. So we have understood what are natural numbers, what are integers, what are whole numbers, what are rational, and now finally irrational. If you come again back to the real number, if you come again back to the number line, here we have just plotted some of the numbers from the sum of the list. Like you are able to see the integers, the whole numbers, the natural numbers, In between somewhere I have marked rationals, and there are some more places which are left which I haven't marked, both for rationals as well as irrationals. Now if I take all those numbers, on this line, if I take all the list of numbers, then they are nothing but real numbers. Fine. So all these numbers come under one category, which is our real numbers, and this is the convention used to denote this bold capital R for the list of real numbers. So with this we conclude today's lecture, and one important information that in the coming lecture we're going to discuss more on how to find two rational numbers, between two rational numbers, how to find a rational number, and some more problems based on both irrational numbers, their representations, and so on. So please do find a link to our Facebook page in the description, and do share about our initiative among your friends, and do subscribe the channel. Thank you so much.